So, ladies and gentlemen, our second keynote speaker is Dr. Claire Krause with her presentation From Satellites to Insights, Tracking Water Across the Australian Landscape. Dr. Claire Krause is the Assistant Director of Product Development in Digital Earth Australia, Geoscience Australia's satellite imagery program. She is responsible for working with our stakeholders to develop ideas and workflows for using the wealth of satellite information to better inform decision makers on Australia's natural resources with a particular focus on water. Claire has a PhD in paleoclimatology from ANU, where she studied the dynamics of Indo-Australian monsoon over the last 40,000 years, using stalagmites from caves and paleoclimate modelling. Please welcome Claire to the stage. Thanks very much.
Well, thank you very much, everyone. My name's Claire Krause and I work at Geoscience Australia. And being in Canberra, I have at least a chance that half of you know who Geoscience Australia is. If you go outside of Canberra, not very many people do. So I just wanted to start by introducing who we are. So Geoscience Australia is one of the government science agencies, much like the CSIRO or the Bureau of Meteorology, except that we're focused on geosciences. We're located in Canberra, and you've probably driven past our building many, many times and not realised. So we're out on the corner of Jerrabomba Avenue and High Marsh Drive, next to the olive grove. We've got that big building out in the middle of a paddock. So it's a lovely place to work. There's lots and lots of free parking. And we have about 600 staff that work there, a combination of staff and contractors. And so we're working on problems in geoscience. So we have parts of our organisation that work in things like the resources sector, understanding Australia's geology and geological history. We look at things like natural hazards. So we have a 24-hour, 7-day earthquake alert centre. So anytime anywhere in our region shakes a little bit, we have duty seismologists who look into that and assess for tsunami risk in collaboration with the Bureau of Meteorology. And one of the other things that we do is satellite imagery. So the program that I work in is called Digital Earth Australia. Go forward, no, too far. And so Digital Earth Australia is a satellite imagery program. So we're using satellite data from the free and open satellites from the USGS and from the European Space Agency program. So we're using the Landsat, which is a 25 metre by 25 metre pixel, and the Sentinel-2 satellites, which are about a 10 metre by 10 metre pixel. And so the Landsat program has been collecting data over Australia continuously since about 1987. So we have an incredible wealth of data, of imagery, of satellite imagery of Australia that we can use to build up a picture of how things on the Australian landscape have changed through time. And in particular, we'll focus on water for this talk. So for this program, what we're doing is we're taking that wealth of satellite imagery and we're actually trying to correct it. So if you can imagine you've got a satellite passing over Australia, there's a lot of stuff between the satellite and the Earth. And so there's some corrections that need to be applied, things like the angle of the sun, depending on the time of the year, clouds and aerosols. And so we correct all of those things to create what we're calling analysis-ready data, which means that you can pick up this satellite archive and instantly start to play with it. So one of the dangers of having that much data is that there are infinite ways that you can visualise and plot and try and interrogate it. But the challenge that we're faced with is turning these 1.2 petabytes at last guess, I think it's probably more because it's collecting new data every day, this 1.2 plus petabytes of data into something that's actually useful. So we don't want to throw an archive of data at people. We want to throw interpreted products, things that are actually useful, that answer the questions that they're trying, that they've asked. So I just wanted to show you the way that we do that by presenting a number of case studies. So ways that we've turned this satellite archive into interpreted products that make it actually useful for people. So here we're on a beach in Brisbane, in Queensland. I think it's just to the north of Brisbane. But if you just keep your eye on that little box that's highlighted there. So what we've done here is we've taken that archive of satellite imagery and we've just turned it into a movie. And what you can see in that little box is a sinkhole. So there was a sinkhole that opened up on this beach in Queensland. And we were sitting in our offices in Canberra and thought, oh, wouldn't it be great if we could see this with the satellites? And so we did some imagery, and you can see it did you see it kind of pop out? And then you can see it come back. And this was really interesting. You know, it's always nice to look at movies of the data that you have. But what you may see is that these sand dynamics going out through the spit. And so here we have that same location, but it's just zoomed out. And what you can see here are some of these incredible sand and coastal dynamics off this particular coastline. You can see where you've got this sand feeding from the south point out into the ocean and actually accreting back onto the coastline in the north. And so we understand that Australia is dynamic. We know that it's constantly evolving, it's constantly reacting. But things like this really start to bring that home, that if we want to start mapping things, we can't think of drawing a coastline and then going away and that's the coastline. We know that it's constantly evolving. And so we can actually use this satellite imagery to start to dynamically map features across Australia. So here's an example of doing that. So this is a river in the Northern Territory, and what you can see here is a dynamic mapping of that channel location. So we've got the oldest shorelines in the yellow colour through to the newest shorelines in the red. And what you can really see is the way that this particular river has moved through the landscape through time. So traditionally, the way that we map things, you would have drawn a river on a map, and that would be it. It would be transcribed, and you'd do an update, and it kind of progress through and be in the same location. But you can see pretty quickly your map will go out of date. And so we're starting to use this data to automatically pull out coastlines and waterlines from this archive of satellite imagery to enable us to create dynamic maps. Okay, so that was one example, and I just wanted to show you another case study where we're sort of starting to go into this idea about dynamic mapping. So we have a product that we've developed called Water Observations from Space, and what that is a water classified satellite archive. So every time the satellite passes overhead, the scenes that come back are run through a decision tree, and each individual pixel is classified as either wet water or not water. And so what you get when you combine that over the 32 years of satellite data that we have is a picture of the frequency of water in the Australian landscape through time. So what you can see, not very well, so I've actually done a little zoom, is the way that the water moves through the landscape. So this is one of those big dynamic floodplains in sort of Western Queensland, Northern New South Wales area through there. And what you can see is the way that the water moves through the landscape is not consistent. Between floods, it takes different channel paths, it floods different areas, and you can start to see where the red colours are the places where it's not seen very often, through to the kind of bluey, greeny colours are where it's consistently seen. And so you can start to build up a picture of the flood history of Australia. Where is water at any given time? Where can we expect it to be? And how does it move through the landscape? And so we've taken this particular product and actually used it to map water bodies. So we've used this product to produce this. So we're across, in this case it's just New South Wales and the Murray-Darling Basin, but literally on the NCI at the moment, I've got a whole of Australia run going, so that'll be hopefully there when I get back to my office. But what you can see here is we've used that Water Observations from Space product, and we've actually used it to draw polygons to map the locations of persistent water. So we've taken out those big flood signals. We don't want to know about those flashy floodplains where water is seen, 1 in 100, 1 in 50 years. We want to know where can you expect water to be at least 10% of that 30-year archive. And so when you start to zoom in, you see how well it's picked up features like these natural lake systems on the bottom left. You've got some rivers through the middle, and then up on the top right, you can see it's picking up artificial structures. We've got some quite linear features up there, and they're man-made dam structures. So the way that we've produced this, very quickly, come and talk to me if you want the ugly version of how it's all done. But so far we've got 87,936 water bodies just for that area around New South Wales and the Murray-Darling Basin. And what we've done is we've taken that Water Observations from Space and we've basically said, okay, where is water at least 10% of the time? So we're removing those flashy floods, and then we've drawn a polygon around it, done some extra filtering to kind of remove things that we don't want. And we've also put a size limit on it. So the water observations from space product has some limitations when you get into wet vegetation, vegetation and water together. So we wanted to remove those very small kind of soggy bits in the landscape, so we've put a filter on that. And what you see is we now have a polygon data set. So the reason that we get so excited about this is satellite imagery is a pixel-based product. And with a picture, one pixel doesn't have a relationship to a pixel next to it. We haven't kind of clumped anything together, and so everything is treated as a separate pixel. By turning this into a polygon data set, we're starting to say, okay, we recognise that these all pixels are actually all part of the same water body. And so we can start to track and monitor those pixels as a whole and understand how that one water body is changing through time. So what it allows us to do is something like this. So this is just a schematic showing the theory of how it's working. So we've got a water body there on the left, and you can see in the red box. And at this particular point in time, we would say that there would be 100% surface area of water. So it's important to point out that with satellite imagery, we're dealing with a two-dimensional picture. We don't have information about volume. So what we're getting is a picture of the changing surface area of water through time. So that is the limitation of this method at the moment. We do have some developmental products where we've started to incorporate things like LiDAR to combine that extra three-dimensional information with our two-dimensional understanding, but that's still early days, so for now it's just a surface area product. So you can see on the left there we have something that would be approximately 100%. The one in the middle you might say is 50, 40%, and then you've got a case on the right where it would be empty or barely anything. And so for every single 16 days from 3 different satellites, you can start to do this classification over every single one of those 90,000 polygons. And what you get back is a time series that tells you how the surface area of water within that polygon has changed through time. So this is an example. It's just a random polygon that I picked out. We have all of this sitting in a web service at the moment, so you can go on, you can click on it, you can pull back the time series and have a look at what it all looks like. And so what you can see on the bottom is what that time history looks like. And so remembering that we're dealing with surface area, the really valuable insight that you get from this is where that surface area changes. So we're looking at when it goes from empty to being full, or when it goes from full to starting to draw down. And so this provides some really interesting insights about how either the water is being managed, if it's a managed system, someone is intentionally pumping in and drawing down, how they're doing that. If it's a natural system, it tells you about things like rainfall and groundwater inflow and how much water is sitting in, for an example, a wetland. Has this wetland been dry? Do we know how long it's been dry for? And if you have water, like the Environmental Water Office, and you're trying to work out where you might want to put it, it provides information about where it's been dry, and then again, once you fill it, how long it stays wet. So we developed this product in collaboration with the Murray-Darling Basin Authority and the New South Wales State Government. And then at the same time, a drought came across New South Wales. So we're still in drought, but this happened in November of last year. And we were contacted by the New South Wales Department of Industry Agriculture to try and help them with an understanding of water availability for stock. They heard that we were starting to map water bodies, and they wanted to know how can we use this information to inform farmers and agriculturalists about the availability of water on their properties and where there might be limitations, whether they can move stock to a certain part of the property and where they might need to get help. And so what we did was we took every single one of those time histories and we started to slice through it. And what that produces is a snapshot of the state of all of those water bodies at any point in time. So at this particular point in time, it was October of 2018 when we did this. And what you can see is that all of those water bodies, or almost all of those water bodies, are red. And red was indicating that they're empty or less than 20% full. And so we plotted this up, and it kind of looks pretty extreme. And so we did the same analysis at a time when we knew that there was a lot of water. So in 2016, there'd been a lot of rain, and so we knew that there was water in the system. And what you can see is that in 2016, you get a lot of blue, and that's what we were expecting. In 2016, we knew that there was water. And so for any single time, at any point in the last 32 years, we can do this kind of snapshot. And hopefully when I get back to my office, we'll be able to do this snapshot for all of Australia as well. So it starts to get to a quantitative indication of water availability and drought severity. You can do comparisons, you can compare to the Millennium Drought, and it allows you to start to understand not just where water is now, but where water has been historically, and the context for our current water availability. So this is now a product that's feeding into the New South Wales Seasonal Conditions Report. And so every single month we redo this snapshot for them and produce a map like this, where you can start to see where water is across New South Wales. Okay. So the water observations from space classifier does a really nice job when you have a very clear water signal from space. If you start to introduce things like turbidity, so very coloured water, or a combination of vegetation and water together, it starts to obscure because the spectral properties of the water are not the same. So what about if we do want to understand where water is in wet landscapes like this here? So this is the Giannini wetlands in the ACT. And so we've got a second product where we've started to combine some extra information. So on this graph here, we have a sum, it's a percentage of that total area. So you've taken the total area of the Giannini wetlands, and we've looked at what percentage of that wetland is these components. So in the darkest blue, we've got that open water, which is the one I was just describing. In the lighter blue, we've got a wet vegetation. So this is using a tasseled cap index, and what that does is it pulls back information about where you have water and vegetation together. In the green, we've got green, happy photosynthetic vegetation. In the kind of brown, the light yellowy brown, we've got dry vegetation. So that's a vegetation that's not actively photosynthesizing. So sort of twiggy bits or dry grass, those kinds of things. And then in the dark brown, we've got bare soil. And so when you combine all of these extra bits of information, what you get is a much richer picture of how this wetland is behaving through time. And we know in Canberra in 2003, we had a very large bushfire come through. And you can see the impact of that bushfire on this wetland, which was burnt, as that big change in behaviour of the wetland right in the middle of the plot. You can see that there's an increase in the amount of non-photosynthesizing vegetation and in bare soil. And what you might be able to see is that the actual dynamics and behaviour of the wetland has been altered by this event. So before that event, you can see there's a really nice cyclicity in the way that the kind of water is coming in, there's a lot of green stuff going on. And then after this event, you can see that that's actually changing. We're starting to get a bit more dry vegetation into the wetland. And you can actually see the amount of water being picked up in the wetland is actually decreased. So this insight is now available for every Ramsar wetland across Australia. And we're also starting to run it for anything. So the value in having a data set that allows you to run code over it is you can just throw a new thing at it and it'll just run the same process. So we're now starting to run that same insight for any polygon that people can kind of come up with that has meaning. And so for now it's Ramsar, but we're also starting to run with some of the state-based wetland polygons as well. This too is available as a web service, so you can open it up, you click on the wetland that you're interested in, and you get back that plot. So it's all available via a website. So where this really starts to become powerful is when you go from policy to actual impacts. So we know that we have a system in the Murray-Darling Basin where the Commonwealth Environmental Water Office throws water down the system to intentionally try and wet things. It's the environmental water, they're trying to target wetlands and make sure that the integrity and health of those wetland systems are maintained. So what we can start to do is provide insight into the effectiveness of those watering events. So what we have here on the bottom of this plot are the timing, duration, and size of some of these watering events that have gone into the Hattar Lakes. And so what you can see here is if you go right to the start of this time series, up the top where we have that combination of that open water and then that wet vegetation and water together, so the open in the dark blue, the vegetation and water together in the lighter blue, if you go right back to the start, you can actually see that there's no water at all recorded in this area. Then, if you look at the bottom in 2013, you can actually see this large environmental watering event that was targeted at this particular wetland complex. And you can see the wet response that happens in this system. So you can start to understand the implications and the impact of these policy decisions that are made. Are they actually reaching the systems that we're hoping them, that we're intending them to reach? And you can see that through all of this. And so again, this provides incredible insight into the success or otherwise of key policy decisions, of things that we are trying to manage in the landscape. Are they actually being managed in the way that we expect them to? So I just wanted to provide a number of little case studies of how we're starting to take this satellite archive and turn it into some useful products. And so if you're interested in any of the work that I've presented, please come and chat to me, because we're always looking to have more polygons and more things that we can start to understand. And the really powerful thing about it is that all of the data that we're dealing with, all of the code is free and open. It's all in GitHub. The data is all free and available, open license. You can put it on a t-shirt and sell it for $10. There's no limitations on it. And everything is open and available. So we're very keen to make sure that people have access to it. Thank you.